When Al Einstein published his general theory of relativity, it was a sensation. It turned Newton's ideas of gravity on its head, saying gravity wasn't a force, but the warping of the space-time fabric. However, Einstein's idea needed confirmation, but the former patent clerk knew that technology in 1915 wasn't sophisticated enough to make this detection. The world had to wait. The wait finally did end in 2015, and with an experiment so extraordinary, Stockholm took notice. But a century is a big gap between idea and confirmation. Modern physics may be headed for even bigger gaps. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and the origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology. And in this episode, as modern physics becomes more elaborate, investment in time, technology, and research stamina grows. But the scientific payoff can be big. The detection of gravitational waves, for example, has confirmed a century-old theory and given us a new means of observing the universe. But are new ideas in physics becoming too difficult to experimentally prove? Find out why it may be your grandchildren's grandchildren who see proof of string theory. Also, do the Nobel Prizes need to catch up with the way modern physics is done? This episode, Too Big to Prove.
In space, no one can hear you scream, but using the right instruments, scientists can pick up all sorts of inaudible cosmic vibrations. After a decade of listening, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the brief chirp of gravitational waves caused by the collision of two black holes.
What happened was a pair of black holes, absolutely massive black holes, banging into each other, merging into each other, stirring up space-time. It rippled across the universe until it came to us after 1 billion years and is now rippling off somewhere else.
Yeah, it was 200 milliseconds, the first event, which is 1/5 of a second, is all that they recorded. What it means is that the black holes, like mallets on a drum, are causing space to wobble. And as they get closer and closer and move faster and faster, they're moving near the speed of light, they scoop up in frequency as the motion gets faster. So it makes this kind of like whooping sound. It happens so fast the human ear can't actually resolve it. You kind of have to slow it down to listen to it.
It was an exciting moment in science. The discovery reverberated around the world. Detecting the brief shaking of space-time earned 3 LIGO scientists the 2017 Nobel Prize in Physics.
But before the early morning phone calls from Stockholm, there were decades of dogged research by scores of scientists, not only those on the LIGO team. Even when the experiment was up and running, there was the waiting. In fact, so much waiting that reporter and physics aficionado Roland Pease confesses his attention waned.
You know, actually, I'd got a bit bored of LIGO because I was thinking, well, these gravitational waves are just too small to detect.
He wasn't the first to despair, because before LIGO, there was a theory of gravitational waves proposed by a chap named Albert Einstein, who later waffled on his own theory on the possibility of their existence. And he was refining ideas about gravity that go farther back, more than 3 centuries.
Imagine it is the 1680s. London is recovering from an outbreak of bubonic plague. The Qing Empire is destined to be the last imperial dynasty in China. Petticoats are a fashion rage. And Isaac Newton is at the top of his game at Cambridge University, where he's puzzling over the nature of gravity.
Gravity is the most keenly felt of the fundamental forces in physics. You experience its thrill when you downhill ski, and its tyranny when you heft a couch up a flight of stairs. Gravity makes mountains crumble, glaciers creep, and it causes the tides. It also holds the universe together.
But why does it? Newton's theory of gravity went like this. Objects are attracted to each other by a force proportional to their mass and inversely proportional to the square of the distance between them. Okay, gravity constrains the motions of the planets, and Newton's simple theory gives you enough physics to predict their orbits. But there was still an annoying puzzle, and Newton was actually troubled by it. Did the force of gravity act instantaneously?
So, for example, if you remove the sun, would the planets know about that right away? Would the Earth immediately stop orbiting the sun, or would it take a while to notice?
Depending on how you answer that question, tells us something fundamental about gravity. For one, it helps us to understand what it is. Einstein addressed that with his general theory of relativity. Now, while Newton thought of space as some sort of fixed stage where things happened, Einstein theorized that space and time were linked and mutable. Distort one and the other responds. So as a consequence, when you remove the sun, it would take 8 minutes before ripples in the fabric of space-time let the Earth know. 8 minutes, of course, is the time it takes for the sun's light to reach Earth, and gravitational waves would travel at the speed of light. The idea of gravitational waves was revolutionary. But was it true? Only experiment could prove Einstein's idea.
And going from theory to experiment would prove arduous.
I'm Jana Levin, and I'm a professor of physics and astronomy at Barnard College of Columbia University.
She writes in her account of LIGO's headline-making discovery, Black Hole Blues, that this unusual observatory was designed to detect not light or radio waves, but ripples in space-time, that colliding black holes would cause space-time to ring like a drum.
Gravitational waves were predicted by Einstein 100 years ago, and even then he went back and forth on whether or not they were real. But this is really the first time we've observed the universe in something other than light. I mean, very nearly everything we know about the universe comes to us from light. We've taken pictures of the sky since Galileo, and so we have this gorgeous silent movie dating back 14 billion years and 92 billion light years across. And this was really something different. It's really like recording the shape of a ringing drum, curves in the actual fabric of space-time. So it's like we're adding the soundtrack to the universe.
Well, from your point of view, was the award for the significance, the importance to science of this measurement, of this discovery, if you will, or was it for the design of this incredibly sensitive device that made it possible?
Well, that's an interesting question. The device itself was clearly at technological advanced capabilities, so that that was already an achievement. Nobody anticipated the Nobel Prize would be given for that. So it really needed to make a detection to succeed. So had nature been stingier with sources, had nature not thrown two black holes together 1.5 billion years ago and sent it our way, then they wouldn't have gotten the prize. So it's in some sense a combination, but the discovery was crucial.
Well, the detection of gravitational waves is important in terms of validating Einstein's general theory of relativity. But if you say that to the person sitting next to you in the restaurant, Einstein is kind of the icon of something incomprehensible, hard to understand, very difficult. So, why should they be excited about it? Why is it important to validate this theory? Because it probably doesn't have too much to do with their daily life.
Yeah, I actually think that's the least important reason to give the prize for this discovery, or the least important reason to be excited about it, if you're asking the person next to you. Nobody really expected gravitational waves would somehow disprove Einstein's theory, or, that was really not a big gamble. I think that instead what it does is it opens up the way that we are able to understand the universe. And this could be like we're on the horizon of a completely new era. Imagine when Galileo pointed telescopes at the sky, all he thought of was the sunspots and the planets. He had no idea there were other galaxies out there, entire collections of hundreds of billions of stars. It displaced us from the center of the universe. It changed radically and in ways almost too huge to summarize how human beings view their place in the universe. And right now we're on the cusp of an era where we might hear things we could never see. We might detect things in gravitational waves we could never take pictures of. And we're opening up the universe again and recognizing that our place in it has to be reevaluated every time we do something like this.
Now, LIGO was successful, as you say, almost 100 years after Einstein first proposed the existence of gravitational waves. That's a pretty long lag. Very few theorists, I think, would be happy to hear that, well, it may be a century before we can do an experiment on your idea here. What accounts for the lag here? Was it just the difficulty of building an experiment that could do it?
It was in part the difficulty of building the experiment, but that only accounts for half a century. The other half a century was because people didn't really know that they were real. And it was argued about whether or not you could get space-time to ring like a drum and whether that would carry energy that could be recorded somewhere else. Even that concept was very elusive and went on for decades. Einstein kept reversing himself whether gravitational waves were real or not real. As late as the 30s, 40s, 50s, this was still going on. In the 60s and 70s, when they started designing these experiments, people still didn't know that gravitational waves were real, and people weren't sure black holes existed. In fact, black holes were incredibly contentious and not very favored by astrophysicists as real objects. So we've discovered a lot in the past 100 years, including that black holes exist. We see evidence of them in the universe all the time, but this was the first time that we've ever detected bare black holes that could not be seen through light. They are just out there, two black holes. They're completely dark against a dark background. And the only way we could ever detect them is by recording the ringing of space due to their motions.
LIGO wasn't the first attempt to detect gravitational waves, of course. There was an experiment run at the University of Maryland quite some time ago, almost half a century now, believe it or not. Maybe you could describe what was being done there.
So you're referring to Joe Weber, who many people cite as the pioneer of this field, but a very fraught character in the history. So Joe Weber was this very ingenious experimentalist. He thought up a lot of incredibly original projects. And he, in the midst of this controversy about whether or not gravitational waves were real, decided, he'd go out and have a look around and see what the universe had to offer and leave the theorists to their debates. And he built an instrument which was kind of like a tuning fork. It was a 3,000-pound aluminum bar, a couple meters long maybe, and the idea was that if space-time was ringing, the bar would resonate in response like a tuning fork, only very, very subtly. And he thought he was making detections daily, maybe from sources in the center of our galaxy. And he presented this work that he had discovered gravitational waves, and the entire community gasped, kind of was struck, and he became an incredibly famous scientist, this important influence. Eventually there were experiments all over the world, literally Italy, Moscow, Scotland, the United States, and nobody heard a thing. So he was discredited, or at least the data did not match with anyone else's. And so this became a very dark period in the history of gravitational waves, where he spent 30 years defending his results and fell deeper and deeper into a kind of disrepute.
Well, when the gravitational waves were detected in, I think it was 2016, Joe Weber's widow, Virginia Trimble, an astronomer in her own right, said that this was devastating because her husband had worked on it with almost no funding until he died in 2000.
Yeah, Virginia speaks really beautifully about Joe Weber's legacy and his work, and she says something really important, which is science is a self-correcting process, although not necessarily in one's lifetime. And I think that's what she felt about Joe's work, that he started something, and even in the detection paper that LIGO, which took another 50 years after Joe Weber's initial claims, and $1 billion and 1,000 people, completely different scale project, even LIGO cited Joe in the discovery paper as the pioneer, and I think that's fitting. But of course, it's painful that somebody is just there climbing Mount Everest and doesn't quite make it to the summit.
Any thoughts about what he was detecting? Clearly, his aluminum bars were ringing. Was it just, trucks in Baltimore?
Well, he had a very careful experiment where he also had bars in other parts of the country so that he shouldn't be getting those kinds of false alarms. So it might have just been the signal to noise, the idea that you're listening for a voice that's so quiet in a noisy cocktail party, and it was just, he was maybe pulling it out of the noise when it wasn't really there.
Jana, it took nearly 100 years between theory and experiment, or confirming experiment. Now, that does seem like a very long time, though, because another prediction of Einstein's general theory, the bending of light, that was verified in a pretty simple experiment in 1919. So that was, only 4 years after the theory was published. Is there something intrinsic in modern physics that makes it very hard to prove?
Well, there's something intrinsic in gravitational waves that make them very hard to detect. So any light that veers too close to a heavy object will follow a curved path because of the bending of space and time. So the experiment that you're describing was facilitated by this beautiful accident that we have an eclipse, and an eclipse is possible from our perspective between the sun and the moon, and that allows this experiment to actually be quite simple and easy. The gravitational wave experiment, on the other hand, the first detection of two black holes colliding, which happened in 2015, the collision of those black holes was the most powerful event detected since the Big Bang, and all of that power came out in gravitational waves. None of it came out as light, and still, by the time the gravitational waves got to the Earth, they rang the instruments by deviations in space-time of 1/10,000th the width of a proton, over 4 kilometers. So this is difficult, okay? This is a whole other level of difficulty, and that's why it took so long.
Maybe you could give a brief description of how you possibly can measure a slight change in a distance that's 1/10,000th the width of a proton. I mean, fundamentally, how do you do that? You don't do it with a tape measure from Sears.
No, you don't. And, my admiration for the experimentalists who made this possible, I mean, this is just, it really is an accomplishment. Whether or not nature had sent us the ringing of black holes, just the technological achievement was incredible. What they do is they suspend mirrors as delicately as possible. And the idea is that if space is changing shape, literally like a wave, squeezing and stretching, that those mirrors will kind of bob on the wave like buoys in the ocean. And what you want to do in your experiment is try to keep track of the location of the mirrors. If you see the mirrors bobbing around, you can record the shape of the waves and the ringing of the drum, to mix my metaphors. And so these mirrors are hung at the ends of these L-shaped detectors, and the arms of the L, literally the letter L, these two orthogonal arms are 4 kilometers long each. And what they do is they send a laser light down that very precisely keeps track of where the mirrors are. It bounces off the mirrors, the laser comes back. If the laser comes back having traveled the same distance along each arm, it will interfere with itself perfectly, in some sense. And if the mirrors bob, so they've traveled different lengths, and they can keep track of that, then they'll recombine imperfectly. And what it allows you to do is essentially record. It's like building, in some sense, a musical instrument around the ringing shapes of space-time and recording the ringing. And it's a very, very subtle, delicate measurement, and yet they were able to do it. It's quite remarkable. And both instruments were ringing, the one in Louisiana and the one in Washington State, which was wonderful confirmation.
Jana Levin, thanks so very much for speaking with us.
Thanks for having me. Good to talk.
Jana Levin is a physicist and astronomer at Barnard College at Columbia University, and she is the author of The Story of LIGO, Black Hole Blues, and Other Songs from Outer Space. All right, so given Einstein's refinement of Newton's theory of gravity, why does a couch feel heavy when you try to lift it up the flight of stairs?
You're buying heavy couches, that's why. Look, the thing is that indeed, Earth is so massive. I mean, compared to most things you deal with every day, Earth is so massive that it really puts a big dimple in space-time. And so that couch is trying to run down the sides of that dimple into the center of the Earth. I mean, it's distorted space-time, and the couch is doing its couchy thing.
And meanwhile, you're trying to walk up that ripple of space-time.
Yeah, exactly. You're pushing against a force. It's like, pushing in a very heavy spring. It takes a lot of energy to push in that spring, and it takes a lot of energy to walk up that hill in space-time.
Well, modern physics may take a lot of brain power. It also includes a collaboration of hundreds, if not thousands, of researchers these days. It's seldom the work of a lone genius anymore. Is it time that the Nobel Committee recognize that?
It's too big to prove from Big Picture Science. The effect of a gravitational ripple is so subtle that the experiment needed to detect it had to be exquisitely sensitive.
That the LIGO experiment was. And so on the 100th anniversary of the publication of his general theory of relativity, Einstein was proven right.
Ladies and gentlemen, we have detected gravitational waves. We did it.
And as California Institute of Technology physicist David Reitz and others pointed out in a press conference, it only took 2 telescopes with detectors that are many kilometers long, 1,000 scientists, 16 countries, more than $500 million, and one spectacular cosmic smash-up to do it.
So these gravitational waves were produced by 2 colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built.
And then, a little over a year after that historic announcement, another.
A lot of us were up very early that morning in anticipation. That's how confident we were that the Nobel Prize would go in this direction this year.
The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Physics, with one half to Rainer Weiss and the other half jointly to Barry C. Barish and Kip S. Thorne, all of them members of the LIGO-Virgo collaboration. And the Academy citation runs for decisive contributions to the LIGO detector and the observation of gravitational waves.
Unlike physicist Jan Levin, BBC science reporter Roland Pease didn't have to get up with the birds to hear the Nobel Prize announcement, but his interest was mixed with ambivalence.
The thing I've never understood is what it is about the Nobel Prizes that make them so mysterious, so engaging, but we all get hooked in.
Mr. Pease enthusiastically follows developments in the field of physics, where he got his own degree. But he is not an unabashed fan of the prestigious Physics Prize. He doesn't dispute that the detection of gravitational waves represents a revolutionary achievement in physics. But he thinks that awarding individual scientists for a collaborative scientific effort suggests that the Nobel Committee may be out of step with how modern physics is done.
He notes ways that Stockholm could more effectively reward scientific advancement, although really nothing can improve upon the electric thrill of scientific breakthroughs themselves.
I always think that the discovery itself was the moment. If you listened to the press conference they had when they announced it, ladies and gentlemen, we have done it. They were so over the moon at that point. And I suspect that most of these people would rather get another extraordinary black hole merger or something weird going on in the deep space than getting a Nobel Prize. But on the other hand, it is a kind of stamp of approval. It says, you are the tops. So, and who could resist that?
And how do their lives change now? And how do their experiments and their pursuit of science change after winning a Nobel Prize?
I think these guys, their scientific life won't change, but what will change is the way that Nobel laureates are mobbed. There's this word Nobelitis, where they get used to being asked questions about all kinds of stupid things, and then the answer's worshipped, and 1 or 2 people go off the rails. They act like gurus, but they will be in demand for everything, and they can probably pick and choose if they feel like it, what they actually agree to do.
Well, I know on some university campuses, for example, at the University of California, Berkeley, you do get your own designated parking spot reserved for NL, otherwise Nobel laureate. So that's one perk.
You know what I'd do, Molly? I'd go and park my bike in it.
Well, Roland, more thoughtfully about the science, what were the accomplishments of LIGO that made the Nobel Committee feel that it was deserving and these 3 scientists were deserving of the prize?
I think the really important bit in LIGO is the O. The G is gravitational waves. The LI is laser interferometry. That's the technique they use to measure these tiny ripples. The O is observatory, and already, just a few weeks ago, they discovered, I think it was the 4th of these events, where they could actually pinpoint as an astronomical observatory where in the universe this actually happened. And so it's a telescope, but it's a telescope that's not using light or X-rays or radio waves. It's using gravitational waves, and that's why you can see black holes, which are the most extreme objects in the universe, and you can see them dance and distort and bend time, and you can't see them properly in any other means. And within about 4 or 5 orbits, possibly less, one swallowed the other. And in this sort of blip sound which they got, that's almost as long as it lasts. Blip. You get the 4 or 5 orbits, one merges into the other. You could work out how much one weighed, how much the other one weighed, how far apart they were, what the orientation was out there in space, whether they were face on to us or not. They could work out that both of them were spinning, which was another thing which they wanted to know. It's extraordinary amount of information they can get just from this. This is just such a brilliant way to explore the universe.
Well, black holes are the monsters of the universe. They're also mysterious and wondrous phenomena. And you are quite excited talking about them. What draws you to the subject of black holes? What do you find so intriguing about them?
The mistake everyone makes is the idea that if there was a black hole in your back garden or something, it would swallow you up. If you turned the sun into a black hole in an instant and it was in the same place and it weighed the same thing as the sun, nothing would change about the Earth's orbit. We would just go on orbiting it. It would be just another gravitational object. The sky would go dark. But if you're right on the edge of the black hole, that's where things become so extraordinary. And so in a funny way, these merging black holes, the first thing you're measuring is they're probing the edge of each other. And that's where all this Einstein stuff comes in, with the curvature of space and things going on, where physics breaks down once you're on the inside of a black hole. So they really are pushing everything we know about gravity right to the limits. And so if you want to know more about Einstein's and the geometry of the universe, this is the place to really test them. How on earth did they get there? How do you get that much matter into the tiny, tiniest space? It's unbelievable. These things have grown or existed within the age of the universe. So there's tons to study, and that's one reason for doing this. And in fact, LIGO will also probe, I think, the Big Bang as well. Just like there's this microwave background people may have heard of, the radio waves left over from the Big Bang, there are also ripples in space-time, which I think they're hoping they will be able to pick out one day with either LIGO, but probably another observatory.
Well, coming back to the awarding of the Nobel Prize in Physics, is it your opinion that it always goes to the most deserving science? And are there scientific projects that lie in the shadows where the bright light of the Nobel Prize Committee never seems to shine?
There are times when you just think, bingo, you've absolutely got it right there in Stockholm. You've nailed this one perfectly. But they're so cautious sometimes. I was massively frustrated. Last year, this prize could have gone to the LIGO project last year, and if it had, one of the devisers, Ron Drever, of the whole project could have had that accolade and known about it, but he died last March, I think, or April. So he's missed that chance. There was no reason. Everyone knew that this was the groundbreaking experiment of the decade, apart from discovering the Higgs. But there was no doubt that this was important. They said that, it all happened a bit too late in the Nobel cycle, if they get the nominations and then they consider them and blah, blah, blah. Push that all to one side. It was obvious. Take the Nobel Peace Prize in 2017. That went to a group called ICANN, who are against nuclear armaments. Their big success was a United Nations treaty about nuclear disarmament that was signed in July. The citation mentions it. They got a prize 3 months later. Why couldn't they be that fast with LIGO? And sometimes they're celebrating things that happened 30 or 40 years ago.
Okay, so I see you have some beef with the Nobel Prize Committee on their timing, but it sounds as though in this case they gave the award to a project that you believe was deserving of it. But are there scientific discoveries that have not received the Nobel that you think should have?
Part of the trouble is that they are slow to get there. So for me, one of the most frustrating is chaos theory. They've never given any prize in chaos theory. It's a completely new flavour of physics that was invented back in the 60s. There are heroes in chaos theory who have died, who really changed the way that we do physics.
Can you summarize what chaos theory is and give us an example of how it changed physics?
Well, take this example. Everyone's heard of this butterfly that flaps its wings in Brazil and changes the weather in Japan. This is the idea that something incredibly small happening in one part of the world could actually have a knock-on effect that get bigger and bigger and bigger until what happens in Japan, you don't know how it got there. You know, a hurricane happened or a typhoon or something completely different in the weather. That's chaos theory. Edward Lorenz, who came up with that, is one of the first examples of chaos theory back in the 1960s, 63 I think it was. He didn't actually mention the butterfly, someone else came up with the analogy, but he has died. And it was an absolutely transformational piece of physics to suddenly realize that really, really tiny things in very, very sensitive systems can have enormous effects. And nature is just full of these. But the Nobel people haven't said, hey guys, well done.
But Roland, what does it matter if, in your own opinion, as you said earlier, you're not even sure what the mystique is about the Nobel Prize and why we get all worked up about these prizes? So why does it matter whether or not they bestow the award to one group or another if you say the Nobels are no big deal?
And I wish they weren't. I suppose that is the thing that everyone knows about the Nobels. There are other prizes that are worth as much nowadays. None of them have this mystique of the Nobels. So it is a way of saying this is absolutely terrific stuff. It carries such a cachet. I don't quite understand it, but if they've got this power, I just wish they'd use it more imaginatively.
Well, what was Alfred Nobel's original intent with the award? Was it acknowledging science? Was it helping to fund science?
Well, it's very much, I think, the latter. I think his original idea was that there are a lot of brilliant scientists who needed money to do research, and why not find the most brilliant young scientists around and say, here's a bit of extra cash, go and build the equipment you want, and you may change the world. So one of the problems with the fact they're so slow making these awards is they often go to people who are in their 60s or 70s. They've actually got 700 other awards already. They're well known to all their peers already. And in the meantime, the young ones are still sort of fighting. If they divided that money up, you know, there are all kinds of fellowships. The Royal Society here in the UK does this. They give people, I don't know what the number is, £100,000 a year to set up a lab in any university they want. They can be there for 5 years or some such number, and they can do brilliant science. If you could give brilliant young scientists a chance to establish themselves and get really interesting science done, the old guys don't really need the honour.
But they do funnel some of their award money back into their labs and into science, don't they?
Yeah, most of them. I've never actually probed too deeply. Most people who get the prize money, they are using it for scientific work of some sort, either to re-equip their labs. You know, they're not greedy people on the whole.
But the odd
I've
one,
not known
maybe
it.
the odd one does go out and buy a new car.
Yeah, you could buy a new car, have a nice holiday. To be honest, you could buy a new house and still have spare change for an electron microscope or two. So most people who get this are actually dedicated to the science. But it's the point, for me, that these are the guys who are at the end of their careers, not the ones who are at the beginning.
Well, Roland, one last area of the Nobel Prize which I'd like to probe, which is the idea of awarding the prize to 3 individuals when there must be 1,000 scientists or so working on LIGO. And I'm wondering if this is the right approach or continues to be the right approach in how the Nobel Prize is awarded, to individuals rather than to a group.
They have to change it. They have to change it at some point. LIGO is a brilliant example. You know, yes, there are 3 key people, 3 or 4 people who you could say they made the difference. But the collaboration, the thousands who are doing it were the ones who made the discovery. You got the same when they discovered the Higgs particle. You know, yes, okay, Peter Higgs and the other guys made the predictions and so on, but the people who discovered it were the thousands, if not tens of thousands, who are working at CERN, making those discoveries possible, all working unbelievably hard to make it happen. And, you know, wouldn't it have been brilliant if the Higgs Prize, it could have gone to Peter Higgs, but it could also have gone to the Atlas collaboration, as it was called, and the CMS collaboration, the 2 detectors at CERN who did the job of discovering it. And they do it in the Peace Prize. The Peace Prize in 2017 went to a group called ICANN. In 1995, the Peace Prize went to a group called Pugwash, who are also anti-nuclear, and to the founding member of Pugwash, Joe Rotblat, who worked with Einstein against nuclear weapons. So the Peace Prize people seem to have got it. Physics is so different from when Alfred Nobel died. Then it really was one or two people in a lab. But some of the big discoveries today involve thousands, and just get modern.
So that's a good slogan for a bumper sticker. So finally, Roland, so what you're saying is that this is something about the LIGO collaboration, says something about how physics has changed in the last 100 years since Albert Einstein came up with his theory that suggested that there were gravitational waves, that we are awarding the prize in a way that we would have 100 years ago, and yet physics has changed quite a bit since then.
We love the idea of the lone genius, and I've seen a lot of comments around this, the lone genius who makes the difference. And some of them exist, but let's celebrate there's so many people who are doing brilliant things, and they can all share in that happiness, and we can share in the fact that it's the science at the end of the day that really matters.
Roland Pease, thank you so much for talking to us.
Thank you so much for giving me the chance to sound off.
Roland Pease is a BBC reporter, producer, and host of Science in Action. Doing modern physics is requiring more stuff than it did in Al Einstein's era. More people, more funding, more time. It paid off handsomely with the detection of gravitational waves, but what does the trend bode for that ever-tantalizing but still unconfirmed idea, string theory?
It's too big to prove from Big Picture Science.
Bringing someone into your organization is kind of like bringing a new pet into your home. I mean, it could be great, but it could be, well, less than great. It's a choice that will have long-term consequences. Hiring used to be definitely dicey, too, with a stack of resumes, endless interviews. But the world has moved on, and so should you, by going to ziprecruiter.com/bigpicture. ZipRecruiter sends your listing to over 100 of the web's leading job boards, but that's just the beginning. Their matching technology scans thousands of resumes and is so effective that 80% of employers who post on ZipRecruiter get a quality candidate through the site within the first day. With results like that, it's no wonder that ZipRecruiter is the highest-rated hiring site in America. And right now, Big Picture Science listeners can post jobs on ZipRecruiter for free at this exclusive web address. That's right, free. Just go to ziprecruiter.com/bigpicture. That's ziprecruiter.com/bigpicture. ZipRecruiter, simply the smartest way to hire. I know this is hard to believe, but living in the world of the Tweety theoretician is not the glamorous life you might imagine. Sure, you can do 3D chess in your head, but to get anywhere in the bespeckled, chalk-herring world of theoretical physics, you got to put your money where your blackboard is. Science is more than just scribbling a theory. You need the oh-so-practical grease under the fingernails, down in the trenches experiment.
I think you need more metaphors. The theoretical prediction of gravitational waves or of the Higgs boson were speculative ideas until verified with experiment.
But the cadence of confirmation seems to be getting slower. Classic case in point. Newton, knocked on the noggin by a red delicious, figured that most everything is governed by just a few laws of motion. So he pens some mathematical equations, writes a book about the results, and then sees them tested, all within his lifetime in the mid-17th century.
But the interval between theory and experimentation has widened. It took a century to confirm Albert Einstein's theory of gravitational waves, and we heard some of the reasons why. Prolonged debate over their existence, and the effort to design the elaborate, sensitive experiment that could find them.
And even then, it was a hefty investment in other resources, numerous researchers, oodles of funding, and the burden of constructing a pair of sprawling research facilities in Washington State and Louisiana. But in the end, the effort confirmed that Einstein was right and has given us a new tool for studying black holes and eventually other cosmic phenomena.
So what is next in modern physics? What big ideas are swirling about, poised to be revolutionary, burning up the pencil lead of theoreticians but still unproven in the lab?
String theory came about in an attempt to do a whole variety of things. One was to unify our understanding of all the forces of nature. The other was to reconcile quantum mechanics and Einstein's theory of gravity.
It's an enticing theory, but theoretical physicist and string theorist David Gross admits that as string theory rapidly approaches its 50th birthday, it's vulnerable to charges of folly.
If you kind of keep pursuing a speculative idea longer and longer and it's not working out, at some point it does get to be a question, are you still doing science?
Columbia theoretical physicist Peter Voigt, in a previous episode of Big Picture Science, was being critical of string theory. He wondered whether it has what it takes to be tested.
I think that's the most controversial thing about string theory right now is string theorists have kind of split into those who are convinced that the theory is well enough understood to believe there really is almost nothing that it predicts, and those who kind of don't want to accept this and say, well, we just don't understand the theory well enough.
It is a wild idea. String theory is a framework to describe elementary particles. It's a way to unify in one theory the fundamental forces in physics: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. It would explain the interactions of big objects subject to general relativity or gravity and small objects governed by quantum mechanics.
Neutrons and protons, fundamental particles, are made up of quarks. And one possible interpretation of string theory is that quarks are held together by being tied to the end of strings. Now, that idea alone takes imagination, but the theory also asks us to accept multiple dimensions to the universe.
Yeah, well, but if we could confirm string theory, it might answer once and for all what the world is really made of. Its potential to do that, and thereby unite the four fundamental forces of nature, have led some to crown it the theory of everything. But Dr. Gross, who is a co-recipient of the 2004 Nobel Prize in Physics for another heady concept known as asymptotic freedom, which describes the asymmetry in bonds between particles, still thinks that, even with the caveat of being difficult to test, the theory of vibrating strings could still become a breakthrough for physics.
You know, if you have a violin string and you can get many different tones out of the same violin string, as it vibrates with different frequencies. A vibrating string can describe a whole bunch of different modes of vibration, and those would look very much, if you couldn't really see the string, your eyes weren't good enough, microscopes weren't good enough, like particles. So string theory has this ability to unify and describe many different particles, maybe all the particles we've ever observed, in terms of different vibrations of a single extended object. Unfortunately, it seems that the distances involved are so small and the energies involved to create these higher energy modes of the string are so big that we can't directly test these ideas.
Some people would say, well, wait a minute, how could a vibrating string give the illusion of something solid? But, of course, maybe something solid just means that they have the requisite forces to resist, putting a weight on them or something like that. I mean, intuitively.
Well, atoms are mostly empty space, as you know. You have the illusion that you are solid, but believe me, you're not. The nucleus of the atoms, which contains most of its mass, occupies only 1 part in 100 millionth of the volume of the atom. The reason they appear to be solid is that your eyes are not good enough to see the individual atoms, or within the atom, the largely empty space in which the electrons surround the nucleus.
I think one thing that people might know about string theory is that the strings themselves, if they exist, are not three-dimensional like most everything else we deal with every day. They can have more than 3 dimensions.
Yes, well, one of the big lessons of this whole approach, which is still in its adolescence, in my opinion, is that we've been challenged to think again about space and time, our most basic concepts of physical reality. One thought is that there could be extra spatial dimensions, which are curled up in volumes which are so small that we can't see that there are these extra dimensions. But, there are other ways where new ideas in physics can play a role. And one of the remarkable advances in the last few years is that these ideas about string theory have turned out to yield insights between the more conventional quantum theories we have of ordinary matter. Some of my friends who are studying superconductors, superconductivity, high-temperature superconductivity, now use these string theory ideas to relate some of the really tough problems in understanding such fascinating materials to, remarkably, string theory in higher dimensional spaces.
Well, you point out that, okay, these strings are really small. We haven't said how small they are, but that would be a number that probably wouldn't mean much to many people. But, if you build a bigger machine, you can see smaller particles because it takes more energy to look inside those guys or whatever. Do you foresee in this century even being able to build, something akin to the Large Hadron Collider, but for looking for strings that we could really see if they're down there? I mean, is that going to happen?
Probably not directly. That's way beyond our capabilities at the moment. But I'm generally very optimistic. If you were to ask me 40 years ago, when people started advancing the notion of being able to build detectors that would detect gravitational waves, I think I would have been extremely skeptical, as most people were. Experimentalists always amaze me with what they're able to think of. So people believed in atoms a century before they were able actually to see atoms, because they were able, assuming the existence of atoms and certain properties of atoms, to understand the microscopic origins of the laws of thermodynamics. 100 years later, we can actually see atoms and manipulate them one by one.
But let me ask you this, it's a bit speculative, but suppose vibrating strings really do exist. If sometime in the future we can somehow prove that, would that be the end of the line, as it were? Would vibrating strings be at the bottom of the totem pole when it comes to understanding matter, or could there be something that makes up vibrating strings?
Yeah, so that's a great question. It's sort of a question as to whether a theory as ambitious as the stringy... I hate to call string theory, by the way, a theory. It's more of an approach yet. A theory truly is something you can test. We're not there yet. But this approach seems to be able to address many of these very fundamental questions. And you might ask, is that the end? Is that the final theory? I'm very agnostic on this point of view. It could be. It could be, just like the exploration of the Earth terminated since the Earth is round, we explored almost all of it. That was the end of exploring the Earth. But it also could be that reality is more like a flat Earth, and once we understand the answers to some of these really fascinating questions we're now asking, new questions will arise, as they always have in the past. The fact that we can't think of those new questions at the moment is because we don't know enough to be intelligently ignorant.
Let me ask you about the Nobel Prize, because you did win the Nobel Prize in Physics in 2004. Did that really change your life? I guess everybody kind of wonders that. Or did it change the way you do science?
Well, it certainly affected my life in the sense that I'm asked to do a lot more things, and I have a lot more opportunities to travel, to speak, a lot of bother. So actually, it is kind of good that they most often give the Nobel Prize after many, many years. They take their time. It's probably very good for science because it does cut down on your productivity.
David Gross, thanks so very much for speaking with us.
It's been a pleasure. Thank you.
David Gross is a theoretical physicist and a string theorist at the Kavli Institute for Theoretical Physics at the University of California at Santa Barbara. He is co-recipient of the 2004 Nobel Prize in Physics. What is happening to modern physics so that these questions are becoming more challenging, more complex, more difficult to test?
Well, I think it's just a matter of the fact that science is a cumulative endeavor, right? You find the big simple things first, and then you start refining your search, and you find smaller, more complex things. It's sort of like biology. 150 years ago, biology was mostly a matter of, looking at plants and animals, stuff like that, and you're figuring, okay, they got lungs and they got, hearts and stuff like that. And then you sort of figure out how those work, and then you look further, and now pretty much you get into cells, and then it turns out inside the cells there are parts, and everything gets really complicated. Now when you look in a book about biology, it's all these chemicals and stuff like that. It's on the microscopic level, and that's, sort of what's happened in physics.
We don't hear enough about those plants with hearts and lungs.
Yes. We have to win the hearts and lungs of plants.
Well, thanks to those who have big hearts and who have proven to be a big help in producing the show. Senior producer Gary Niederhoff, operations manager Barbara Vance, and intern Daniel Marino.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bose Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and educational organization whose scientists study the origin and nature of life and the behavior of comets and asteroids. And a big thanks also to our listeners.
Your ears have been attuned to an episode of Big Picture Science called Too Big to Prove. If you want to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because you have hopes of building a 6-transistor gravitational wave detector, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like this show.